In this session, we will discuss about FFT algorithm for n equal to 2 and n equal to 3. The objective of FFT is to illustrate FFT calculations mathematically. At the end of this module, students will be able to develop FFT flow graph, compare DFT and FFT computationally, perform forward and inverse FFT, plot signal spectrum in frequency domain. So let's start with FFT flow graph for n equal to 2. By discrete Fourier transform, x of k equal to summation of x of n wn raised to nk. In this expression, let's put n equal to 2. So x of k equal to summation of x of n wn raised to nk, n varies from 0 to 1. Expand this summation term. Let's evaluate this for k equal to 0. We get x of 0 equal to x of 0 plus x of 1. And at k equal to 1, we get x of 1 equal to x of 0 into wn raised to 0 plus x of 1 into wn raised to 1. We need to calculate wn raised to 1. To calculate this wn raised to 1, we'll start with basic definition of w term. Let's put n equal to 2. So this is e raised to minus j pi, that is cos pi minus j sin pi. Cos pi is minus 1 and sin pi is 0, and therefore wn raised to 1 is minus 1. By substituting wn raised to 1 equal to minus 1, we get x of 1 equal to x of 0 minus x of 1. X of 0, x of 1 are input values, and x of 0, x of 1 outside, these are coefficient values of discrete Fourier transform. Now, let's evaluate this DFT equation and we'll get these required coefficients of DFT. We now want to evaluate this graphically. So to evaluate this graphically, left hand side x of 0, x of 1, these are discrete time sample values, and output side, right hand side, x of 0, x of n, these are coefficient value. So to calculate the first output value x of 0, we have to take small x of 0, small x of 1 here and add them together. Resultant value x of 0. Similarly, to find x of 1, let's take x of 0 and then we'll have to subtract this x of 1 from this x of 0. So we'll have to multiply this x of 1 by minus 1. X of 1 multiplied by minus 1, resultant value is x of 1. This is the FFT flow graph for n equal to 2. Similarly, to find FFT flow graph for n equal to 3, let's start by DFT equation. Put n equal to 3, expand this summation term and evaluate this equation for every value of k. First value at k equal to 0, it is summation of all the input numbers. At k equal to 1, we get x of 1. At k equal to 2, we get x of 2, and so on. All these equations we have to implement graphically. Left hand side input, right hand side output. The first output value is x of 0, and that is summation of all the input numbers. This x of 0 plus x of 1 plus x of 2, resultant value x of 0. Second equation, x of 1. To find this x of 1, x of 0 multiplied by wn raised to 0, wn raised to 0 is 1. X of 1 multiplied by wn raised to 1 added here, x of 2 multiplied by wn raised to 2, resultant value x of 1. And the last expression for x of 2, x of 0 plus x of 1 into wn raised to 2, x of 2 plus wn raised to 4. This is FFT flow graph for n equal to 3. Radix to Coulomb-Touquet's decimation in time fast Fourier transform algorithm. FFT flow graph was developed by Coulomb-Touquet. Two scientists, Coulomb and Touquet. In 1965, James Cooley and John Tukey published a paper describing the fast Fourier transform algorithm which led to an explosion in digital signal processing world. Their landmark research offered enormous improvements in processing speeds and played an essential role in the digital revolution. Thanks to James Cooley and John Tukey. Radix 2. Radix means base. Your base is 2. Decimation in time fast Fourier. So let's derive this DIT FFT equation. By discrete Fourier transform, x of k equal to summation of x of n wn raised to nk, here n varies from 0 to n minus 1, where x of n is x of 0, x of 1, x of 2, x of 3 and so on. Here we will take x of 0, x of 2, x of 4, x of 6, that means x of n only for any1 in the first summation term and x of n only for n odd in the second summation term. So this summation term will divide into two parts. In the first summation term, we will replace this n by 2r, and in the second summation term, we will replace this n by 2r plus 1. So here, this equation becomes x of k equal to summation of x of 2r wn raised to nk, n replace it by 2r, that is wn raised to 2rk, and in the second summation term, n is replaced by 2r plus 1k. Let's expand this w term. In the first summation term, we'll take x of n only for any1, and that we get when we put r equal to 0, that is x of 0, r equal to 1, x of 2 and so on. Similarly, in the second term, we get x of n only for n odd, 1, 3, 5, 7, like that. Now, one by one, we will expand this summation term. wn raised to 1 is e raised to minus j 2 pi by n. That means wn raised to 2 is wn raised to 1 to the power 2. But wn raised to 2 is e raised to minus j 2 pi by n to the power 2. Let's replace this n denominator n by 2. And outside this power 2, we'll take it inside. So this pi will get multiplied by 2 pi. Now, wn raised to 1 is e raised to minus j 2 pi by n. Here it is e raised to minus j 2 pi by n by 2. This n replace it by n by 2, and therefore this bracket term is wn raised to 1. So this bracketed term will become w of n by 2 to the power 1. N replace it by n by 2. And therefore wn raised to 2rk is w of n by 2 to the power rk. Similarly, the second w term will simplify it, and we get w of n by 2 to the power rk into wn raised to k. That we will substitute in this expression. So by simply substituting the simplified w term, we get summation of x of 2r w of n by 2 to the power rk. Similarly, here summation of 2r plus 1 w of n by 2 to the power rk into wn raised to k. In this entire expression, are variable parameters. In the summation term, variable parameters are. Here r varies from 0 to n by 2 minus 1. In this w term, there is no varying parameter like r. That means wn raised to 2k is a constant term that will take it outside. This is DFT of x of 2r. And the second summation term is DFT of x of 2r plus 1. Let's call it DFT of x of 2r as g of k and DFT of x of 2r plus 1 as h of k. So g of k is n by 2 point DFT. So we have two options to find x of k. One is by DFT equation and second by DIT FFT equation. In the DIT FFT equation, g of k is n by 2 point DFT and h of k is n by 2 point DFT. So total computations required to find x of k by DFT equation is n square, whereas total computations to find x of k by DIT FFT equation is three-step procedure. First, we'll have to calculate g of k. G of k is DFT of x of 2r. To calculate g of k, we require n by 2 square multiplications. To calculate h of k, we require n by 2 square multiplication. And then all these values will have to add it one by one. Addition will give corresponding value of x of k. This equation we have to evaluate n number of times. That means n number of times we'll have to multiply w raised to k with h of k, and that value will have to add. W raised to k will have to multiply with h of k values n number of times to get n values of x of k. So this will be addition of n multiplications in the expression. For n equal to 8 by DFT, we get 64 multiplication. For n equal to 8, complex multiplication by DIT FFT equation is just 40. 40 is less than 64. That means calculations are reduced. So here, to find DFT x of k by DIT FFT equation, we decompose x of k, n point x of k by 2 n by 2 point DFTs. So our conclusion based on this discussion is DFT calculations are reduced when we decompose n point DFT into n by 2 point DFT. In other words, decomposition reduces calculation. If you want to reduce the calculation further, you have to keep on reducing and reducing. But question is how long we have to continue this. Very simple, as long as it is possible to continue. For example, when n is 8, we decompose into 4.4 point. 4 point DFT decomposes into 2.2 point. 2 point DFT cannot be decomposed further because 2 is an discrete time signal at n equal to 0.5, that is at t equal to 0.5 ts. We cannot get a definite value. We cannot get a confirmed value. That means it is not defined. So discrete time signal is not defined for non-integer values of n because there are multiple possible values. It is defined only discrete instant of time. In simple words, it is defined only for integer values of n.
Coursera is an online learning platform designed to provide high-quality structured education in a flexible and accessible way. The platform offers academics and professional courses across science, technology, engineering, and management. Visit www.coursera.in. Midnight Masterclass is a YouTube channel, and we welcome you to Midnight Masterclass, your late night destination for learning that is actually fun.
Thank you.